is on compound interest, more specifically looking at future values. So in this section I'm going to do a bunch of different examples in relation to future value. If you follow through with as many of them as you can, it'll give you a little bit more practice and a few more examples to work with. But there are quite a few examples that I'm working through, and then I'm also partway through this lesson going to show you how to do this on the graphing calculators using the TVM solver function. So there are a few definitions that we need to know, and there will be quite a few examples for this section. So our goal for this is determine the future value of an investment that earns compound interest. So if you remember from the first two sections, simple interest means that that interest is just being paid on your original principal amount, not compounded on the interest that's being earned. So compound interest means that you have your investment or your loan, whatever it is, and you pay your paid interest or you pay interest on your interest. So something is compounded annually. That means that the interest is determined or paid yearly. A compounding period is the time over which interest is determined. So interest can be compounded annually, semi-annually, so that's twice a year, every 6 months, quarterly, which is every 3 months, monthly, weekly, or daily. Sometimes you'll get bi-weekly as two, which would be once every 2 weeks. The rule of 72, it's just a simple formula for establishing the doubling time of an investment. 72 is divided by the annual interest rate as a percent to estimate the doubling time of an investment in years. So the rule of 72 is most accurate when interest is compounded annually. So it's just basically a little trick that you can use that gives you an estimate about as to how long it would take for an investment to double. So if you invested $1,000 at, say, 10%, how long would it take to double to 2%? So you would divide your interest rate by 72, and then the time that you have, the value number that you're left with is how many years it would take to do that. So it says Yvonne earned $4,300 in overtime on a carpentry job. She invested the money in a 10-year Canada savings bond that will earn 3.8% compounded annually. So once a year, it's going to be applied to that loan. She decided to invest in the CSB instead of keeping the money in a savings account because this CSB will earn more interest. So putting that much money into just a regular interest account or savings account in your bank, whatever, if you use a bank or a credit union, generally the rates are very, very low on that. So by actually investing it in something, you get a better rate of return. So it says, what is the future value of Yvonne's investment after 10 years? So from the last section, we know that what we're looking at, our A value, is going to tell us the amount that we have, or that we will earn. And we had two formulas that we looked at. Oh, and I'm missing my set of notes here, but we had two formulas that we looked at when we were calculating interest. So one of those was just the simple interest formula. I is equal to the PRT, and then the second formula we used was that for future value A is equal to P plus PRT, or A is equal to P times 1 plus RT. And your A stands for your future value. So either formula, A is equal to P plus PRT, or A is equal to, so if I GCF that P out of there, it's 1 plus RT. So, if we take a look at this, using either formula, so we know our A is what we're trying to find. Our principal amount that she was investing was $4,300. Our R, so our interest rate, was 3.8%, and our T was our time, So that is our time in years. How much will she earn in a year? Because remember, it's compounded annually, so the interest is only applied once a year. So if you did it this way, using our formula, we would have A is equal to 4,300 plus 1 plus our R was 3.8, and we should change that into a decimal because that was 3.8%. So 0.038 times 1. So this is 4,300 times 1.038. So that is 4463.40. Okay. So this first part said using reasons about the compound interest rate formula, so that's what we have done. So if we are taking a look then to see how much this would be at the end of 1 year, which she would have, at the end of 2 years, she would have that 4463.40, so that's the amount of money she now has because it's being compounded. We're earning interest on the interest, so then we would multiply it by that 1.038. So at the end of the second year, she would have 4,630, whoops, should be 33, rounded. So then if we wanted to know how much she earned in the third year, we would do 4,633 times 1.038 because that's her rate of interest. But that's going to take a long time to go all the way through there till we get to year 10. So if we continued with that, and yeah, I left you some room here. So if I would do it for year 3, as I was saying, year 3 would be $4,633 times 1.038, and we get that amount, which would be 4809.06. So if we think about this, what we've done is we've multiplied, every year we've multiplied our amount by 1.0338. So for year 3, what we've done is we've taken our initial investment and we've multiplied it by 1.038, 1.038, 1.038, right? That's what we had done to get that value. So this is the same as saying 4,300 times 1.038 to the power of 10. Not 10, 3, because we've done it 3 times. I'm jumping ahead here. So if I've done that 3 times for 3 years, then that makes sense that for 4 years, I would be doing that 4,300 times 1.038, the rate of interest, to the power of 4. So if I wanted to get all the way up to 10 years, then what I would do is multiply that 4,300 by 1.038 to the power of 10. And that would equal 6243.70. So on your calculator, what you could have done is went after A3, 4809.06 to find the 4th year, then you'd multiply by 1.038. Whatever that equaled, you multiply by 1.038 to get what you would have at the end of year 5, and keep going doing for year 6 or year 7. Or this would be the short way of doing that. So really what we've done there is we've taken our principal, so A is still our future value. What we've done here to find our future value is we've taken our principal and we've multiplied it. So P is your initial investment or your principal. Our I, so our interest rate, inside here, to get that we went 1 plus whatever our interest rate was. And interest and rate are the same thing. They're kind of interchanged in the formulas. So our I is our interest per compound period. And that's key. It's per compound interest, per compound period. Because if it's said that you earned 5% interest and your interest is compounded semi-annually, that would mean it'd be twice a year. So they take that 5% and divide it 2.5 for the first half of the year and 2.5 for the second half of the year. Not 5% for the first half, 5% of the second half. And that's where people make mistakes. So your interest is always per compound period. So if it said it was compounded monthly, then you divide your interest rate by 12. And your n then, because what we did here is we put that all to the power of 10. So if we call that our n then is our number of compounding periods. So if you were doing it annually for 10 years, that means we would have 10 periods. If we did it semi-annually for 10 years, then that means you would do it twice a year for 10 years, so you'd have 20 compounding periods. So n is the number of compounding periods. So this is our formula that we're going to be using when we're looking at future value for compound periods. There's simple interest periods where you're just earning interest strictly on your principal amount, then you wouldn't use this formula. So the next part says, the compound interest rate I of an investment at the end of any compounding period is the difference between the value of the investment at the time, A, and the original principal, P. So all they're saying is, if you want to know how much interest you've earned, you take a look at your present value that you have or your future value that you've calculated, which is A, and you subtract your principal, your initial amount you invested. So it says, how can this relationship be represented symbolically by using the variables I, A, P, and I? So if I is the amount of interest you earned and little I is your interest rate, how could we substitute that? Well, we know our A value here is, from our formula we just developed, is P times 1 plus little I to the n, and then minus P, which is our principal. So if I wanted to do a GCF, I could GCF a P from here and a P from here. So we'd have I is equal to P times 1 plus I, I'm going to put that in brackets, to the n, minus 1. So B, it says, for Yvonne's investment, the number of compounding periods in the term was the same as the number of years. Suppose that the interest has been compounded semi-annually. How many compounding periods would there have been at maturity? Explain. So semi-annually means that there was two per year. I'm just going to pause for a second. Okay, so if it's 2 per year, then if we want to find out how many compounding periods there would be at maturity. So 2 per year for 10 years would be 20 compounding periods. So if we wanted to figure out then how much would she make, if our principal here is the same thing, so she's investing that $4,300, our interest rate then was at 3.8%, so 0.038. But remember, the interest that we're looking at then is per compounding period. So if we have 2 every year, that means we have to divide that by 2. And then our n is our number of compounding periods, so we calculated that out to be 20. So using that formula then, A is equal to P times 1 plus I to the power of N. At the end of 10 years, our 4,300 would be 1 plus 0.038 divided by 2, and you could just write that as 0.019 to the power of 20. So this would be 4,300 times 1.0, whoops, not 00, just do 019 to the power of 20, which would be 8,000, no, sorry, that should be a 4, I just can't read my own. No, it's a dollar sign. 62,465.45. That doesn't seem right. I think I put in an extra digit there. And of course I don't have a calculator here with me. I'm just going to do a quick check here to see, because it should be in the 6,000s, but I don't think it should be that high. So let's see. 4,300 times 1.019 to the power of 20. 6265, I put my decimal. 62, I put an extra 4 in there. That was my problem. So 6265.45. There we go, that's better. So by compounding it that extra time, oh, my answer is on the other page, I think, isn't it? Oh no, it's up here. 6243.70 was when it was just done once a year, and 6265. So it gives you an extra about 20, just a little over $20 interest in that 10-year period. Which over 10 years isn't much, but if you leave your money in there longer, then of course you're going to be earning more interest on the interest that you invested, and you'll have that much more money. Okay, so let's try a couple more. Martha has invested a $23,000 inheritance in an account that earns 13.6% compounded semi-annually, so that means twice a year. The interest rate is fixed for 10 years. Matt plans to use the money for a down payment on a house in 5 to 10 years. So, first thing we need to do, it says, what is the future value of the investment after 5 years? What is the future value after 10? So, knowing that our A, that's what we're trying to find, is our future value. Our principal, so the initial amount was $23,000. Our I was 13.6%, which is an incredibly high rate. So that would be 0.136 compounded semi-annually, so we divide that by 2. And our N, depending on the number of years we're looking at, so if we look at the 5-year one, so if it's 5 years, twice a year, that would be 10. So this is for the 5-year loan. And if we're doing this exact same thing for the 10, I'll do it over here, our principal would be the same, our interest rate would be the same, but our number of years that we invest would be, our number of compound periods would be 20 instead of 10. So for A5, so our principal was $23,000 times 1 plus 0.136 divided by 2, and this is to the power of 10 because it's 5 times 2. So at the end of the 5 years, they would have $44,405.87. If they left it in there for the 10 years, then they would have the 2,300 times 1 plus 0.136 divided by 2, and then to the power of n, which was 10 times 2, so 20. So that equals $85,733.96. So easily twice plus a little bit more money if he leaves it in longer. So it says compare the principal and the future value at 5 years and 10 years. What do you notice? So at 5 years, your initial investment went from $2,300 to $4,400. So at 5 years, it's almost doubled, because doubled would be $4,600. At 10 years, we've gone from 23 to 84. So that's a little less than quadrupled. It's about 3.5, 3 3/4 the amount that you initially started. So it's almost quadrupled. So then it says, if the investment had earned simple interest, would the relationship between the principal and the future values have been the same? So after 5 years or after 10 years, if this had been a simple interest calculation, would we have the same amount? So our simple interest, remember, is that principal times rate times your time. So after 5 years, we would have, not 43, 23,000 times our rate of 0.136, and our time was 5 years. So we'd have $15,640 in interest in 10 years. So our $2,300 investment would be worth $38, and in 10 years, it would be 23. Oops, that should be 1,000. Did I do that wrong on the other one? I might have. Times 0.136 times 10 for our 10 years, which would be 31,280. And if you notice, that's just our 5-year interest times 2. So in the simple interest one, a 44 to an 85 was more than times 2. So why is this different? Why didn't we earn, why didn't our investment double or quadruple? Well, it's because simple interest pays interest only on the principal, not on your future values. Or not on your interest, I mean. So simple interest pays interest only on your principal. Whereas future value pays interest on the interest earned every year. So simple interest is going to be less because you're not compounding anything on that interest that you've earned on your investment. So the next section here is determine future value of investments with monthly compounding. So monthly compounding means that you're doing it 12 times a year. What we're going to do for this one is I'm going to show you how to do these ones on the graphing calculator. So I'm going to go through some examples on the graphing calculator, and then we'll come back and do this one. So the first part is just to show you what each of those keys on the TVM solver does, and then we'll do a few questions with them, and then we'll come back and finish this one up. Okay, so you have this page in your booklet there. It looks a little bit different than mine because I got rid of a couple of the headings, but it's the same basic stuff. So on your TVM solver, when we go to, and this is Well, I don't have the screen up yet. I'll come back to the screen in a second. When we go to the TVM solver screen, what you need to know is what each one of these symbols stand for. So N, capital N, and they don't use the exact same thing as they do in our notes. So that's why I'll go through each one of these. So N is your number of payment periods. So if it was 10 years compounded semi-annually, that means you'd have 20. Your N would be 20. Your I% is your interest per annum. So the interest that you're earning every year. So in that last question, the interest per annum would have been that 13.6%, I think it was. PV is our present value. So similar to what we would call our principal. PMT is going to be a function that we use when we want to calculate, say for example, a loan, how much each payment would be. So PMT will compute the amount of each payment. FV is our future value. So that's the equivalent of A, and this is the equivalent of P. So future value of investment or loan. Your P/Y is the number of payments per year. So this is similar to our N value in that future value calculation of compound interest. CY is the number of calculations or compounds per year, compound periods. So if it says it was bi-weekly, then you would have 26 periods per year that you would compound your interest. And then PMT is basically your end result. Payments made at the end of a certain period. If you're looking at the end, or the end value, so if you're looking at it at the end, it's the payments made. At the end of a certain period. Or if we're looking from a beginning standpoint, it means the payments made at the beginning of a certain. So if you're, say, like down payments, if you're putting in a down payment, you put that on at the beginning of an investment. Oh, there should be made. So at the beginning of a certain period. Okay, so those are the symbols that we're going to come across. So we're going to try a few questions with this. So it says, if you've invested $1,000 for 8 years at an annual interest rate of 2.95%, what would the future value be if the investment was compounded annually, quarterly, and daily? Okay, so what you need to do on your staffing calculators, we go to the apps button, which is depending on which, this is the TI-84 edition. So if you have the TI-83 edition, it might be a little bit different, and I don't have one with me to see what it is. But this APPS button, and you get a screen like this. It says Finance, Algebra, Alg 1, PR2, and so on. Well, we want the finance one, so we're going to select number 1. Then it says Calc Vars TVM Solver. Well, that's what we want, is the TVM Solver, so you can just hit enter or 1, doesn't matter. Okay, and then you have your screen. I'm just going to change this because it's, yeah, let's do this way. So you can just see the buttons that I'm hitting, and it'll change it on here. I found that really hard to look at. So for this particular question, it said if you invest $1,000 for 8 years at an annual rate of 2.95%, what would the future value be? If the investment was compounded annually, quarterly, and daily. So our end value that we're looking at, because it's over 8 years, is going to be 8. I'm just going to pause for a second here because I think there's a way I can show you both at the same time. Okay, I think I've got it here now, so I can have both pages up and you can see what I'm doing. So based on the information here, we know that our N is equal to 8, so this is for annual. N is equal to 8. Our I, so if you remember, I was our interest per annum. So the interest for this question was 2.95%. And because it shows it in a percent there, we leave it as a percent. We don't change it to a decimal. Our PV, so PV is our present value. So the amount that we're putting in is $10,000. But we put a negative in front of there because that's what our investment was. So we're taking, if you think of it as being taking 10,000 of our money and putting it in there, so we put that as a negative 10,000. Our PMT, so PMT calculates the amount of each payment. We're not worried about that, so we just skip over it. Future value, that's what we're trying to find, so we just leave that one for now. The payments per year is at 1 already, and we're doing this annually, so we don't need to change that for annual, as well as our C per Y, which is our compounding periods per year. Well, because we're only doing it once a year, it is a 1 too. It's a 1 also. So once we have put those things in there, so I put this is 8. Oops, I can get rid of that. I go down. My interest rate was at 2.95. PV, so that is our present value. So we're negative 10,000. Our payment, we're skipping over that one. Oops, skip over that one. Future value, that's what we want to calculate. Our payment per year was 1. Our compounds per year was 1. So now what we need to, and we want to know what this is at the end. So now we go back up to, whoops, I went too far. Back up onto future value. And then we hit, just going to mess this up, okay. No, it's not going to let us show you. Okay, this is where I am. Okay, so I moved back up to future value. Then I hit the green alpha button. Our alpha is flashing at A, so we leave it at A, and then we hit enter, and our future value is calculated as 1,201. Let me try that again. $12,618.59. I can't get my. keypad going there. So keypad, your key press history. So the key here is once I've entered all of these things, go back to future value. So these ones, oops, I better write those other ones in here too. So we skip payment. We skip future value. Our payment per year was 1, our compound per year is 1, and then we go back to future value, and then the button we press after that was alpha, and A is flashing, so then it was just enter. So for the annual amount, our future value was $12,618.59. So to do this quarterly, so quarterly, same idea, but what we need to do here for quarterly our interest rate is still 2.95%. Our present value stays the same. Payment stays the same. So we need to go to future value here and change that to a 0. Payments per year. Same thing, it's doing it once a year. We're only getting paid once, but our interest is being calculated quarterly. So our calculations per year is equal to 4. So we're doing it once a year, but we are, it's 1 year's worth, but it's 4 times per year. Again, we're on the end. So once I've done that, I go back up to future value. Sorry, my microphone doesn't want to stay on my ears. Okay. So then I go back up to future value. And that's when I do the alpha button, and then enter. So my F value will equal, so if I go back up to here now, future value, hit the alpha button, hit enter, and I get $12,650.78. So the next one was to do it daily. So for daily, it's the same thing. My number of years that I'm doing this for is 8 years. My interest is the same. My payment value or the present value is that $10,000. Change this. Well, you probably don't even have to change it, but we'll see. So if my calculation then per year is now gone to 365. So after that 65, I go to the future value, alpha, and enter. So I change that one to 365 because they're doing it daily. Go back up to alpha, to future value, alpha, enter, and I get 12,000. $12,661.62. So it makes a difference if you're calculating your interest, especially when it's being compounded daily. I'm going to clear this, and I have to skip pages over here, so I'm going to have to move this a little bit, and we'll go to the next one. So we're going to do the same type of thing, just some different questions. I wish I could make this a little bit smaller, but it won't shrink for me, will it? No. Too easy. Okay. So, next question says, and I'm going, actually this one, because it was the same as the other question. Oops. Oh, there we go. I need to have my screen there. Oops, I need a little bit more. I need my bar. Okay, so I'm doing example 3.4. Okay, so it says, Bill wanted to know how much money he would have to invest in an RESP so that he could have $10,000 for his son's university education. The RSP he was considering paid 4.75% compounded annually, and the length of time would be for 18 years. So in this question here, what we're looking at then is what will the present value be? We want to know what does he have to put in there right now in order for him to have $100,000. I think I said 10,000 initially. So our number, or N for this one, I don't think it'll let me clear everything. I think I have to go to each one and clear it. Does one move up? Okay. So our number of years then is 18. Our interest percent, so it says he's investing this at 4.75%. Present value is what we're trying to find because we want to know how much it will be if he puts that in there. Payments, again, we're not asking to find the payment, so we just leave that at 0. Future value, so we want to have $100,000. Payments per year, because this one says it's being done, number of payments per year, it's only being done once a year, so that's a 1. And our compounds per year, again, it's just once a year. So for this one now, when we do this in here, our future value, we want to have $100,000. Payments per year was 1. Our compounds per year is 1. We need to go back up to the top here. Number of years was 18. Our interest was 4.75. Our present value, let's just put a 0 there for right now. Payment was 0, so we've got all those. So because we want to find what is the present value, that's where we want to do our alpha. So at present value, we hit alpha, and then we hit enter. So I'm on present value, cursor is flashing there. Alpha, enter, and it tells me that I'm going to have to take from my own money $43,373.80 in order to have $100,000 when I am all done. Okay, the next question here says, Mike wants to know, nope, not going to let me move. Mike wants to know how much money he would have to invest in a CD that pays 2.75% annual interest compounded semi-annually so that he would have $25,000 to buy a new boat. So CD is just another type of investment. So for this one, the number of years he wants to buy a new boat in 5 years. His interest that he's going to be earning is 2.75%. Our PV, so that's the present value. He wants to know how much he has to start with. Payment, again, we're not worried about that, so it stays at 0. Future value, we want to have $25,000 when we're all said and done. Payments per year, just 1. It's an annual. But our compounds per year for this one, because it's being compounded semi-annually, that means we have 2. So if I go up to the top here, my 18 turns to 5. My interest rate was 2.75. Future value, let's put that at 0 for now, or present value, I mean. Payment is 0, future value, so we want to have $25,000. It's being paid once a year, but our compound periods are 2. So now go back up to PV, hit your alpha, enter. So alpha, enter, and it tells us that we would need $21,808.78 to invest. Okay. The next page. So the question says, Ashley and her husband want to buy a house in 5 years. They will need a down payment of $40,000 to purchase the home. If they have $25,000 now, what rate compounded annually would they need to have if they invested the $25,000 to have enough for the down payment in 5 years? So we want to know how much what interest rate do they need to have in order to make their $25,000 grow to $40,000? So for this one, our number of years, they want to know in 5 years, they've got 5 years to gather this money. What is the interest rate that they will need if they invest that $25,000? So they're taking their $25,000, so it's always a negative. We're not worried about the payments. Future value. They want to have $40,000 when they're done in 5 years. It says the rate is compounded annually. So those are both ones. You sneeze. Okay. So number of years is 5. We don't know the interest, so we're going to move up there and just put a 0 for right now. Present value, they're investing $25,000 of their own. Payments are 0. They want to end up with $40,000. One payment per year and compounded once a year. So we go back up to the interest, hit the alpha, enter. Oops, that should, oh my goodness. Try that again. So it was alpha, enter, and it has 9.8560. So basically 9.86% is what they need to invest. Okay, the next one. What rate of interest would you need to have to take $35,000 and turn it into $65,000 in 12 years if the investment was compounded quarterly? So our number of years we have for this one is 12. We're trying to find our interest. Present value is negative $35,000. Our payments stays at 0. Future value, we want to have $65,000. 65? Yeah. Payments per year is 1, but our compounds per year it's quarterly, so that is 4. So up at the top there, we're doing this for 12 years. Don't know our interest. Present value is negative $35,000 that we're investing. We want to end up with $65,000 in the future, and compounded 4 times a year. Go back up to interest, alpha, enter, 5.19%. Next one says, how many years would it take for a CD deposit of $25,000 to double if the annual rate of interest was $4,000 compounded weekly? So this one, we need to find our N. So we don't know how many years this is going to take, but we know our interest is 4%. Our present value, so we're investing that negative $25,000. Payment again is at 0. Future value is, we want to double it, so it's $50,000. Payments per year is 1. Compounds per year. So this one is being compounded weekly. So there are 52 weeks in a year. So our N is at 0. Our interest was at 4. We're investing, of course we can't have the same, we have to change it every time. 25,000. Payment is 0. We want to end up doubled, so 50,000. And we're doing this weekly, so it's 52. So once you have those values in there, you go back up to your N, alpha, enter, 17.33 years. Okay. So I've kind of done one where you're finding each one of those, where you're finding your number of years, your interest, or your future value, or your present value. So now you can pretty much tackle any of the other problems that come up. So I'm going to go back to your notes, or the regular notes, and do a couple of the examples that are on there. Okay, so for this one, let's clear some of our history here. Oops, I went too far there. Okay, so it says, we're trying to find future value with monthly compounding. So both Jolie, age 50, and her daughter, oops, I'm stuck. Lena, age 18, plan to invest $1,500 in an account with an annual interest rate of 9% compounded monthly. If both women hold their investments until age 65, what will the difference in future values of their investment be? So we're going to do it for Lena, and then we're going to do it for Jolie. So our number that we are looking at, so our N, remember, is the number of compounding periods that we have. So if we are looking at, it's for Jolie, she's going from 50 years, or so, from 50 to 65, so she's got 15 years that she'll be doing it for. So this is Jolie. Her N is going to be 15 years, because that was 65 minus 50, so 15 times compounded, and it says that this is being compounded monthly. Our interest that she's earning is 9%. Her present value, she has invested $1,500. Future value is what we want to find out. Our payments per year then, because she's being paid 12 times, it's monthly for this one. So her payments per year that she's getting is 12, and her compounds per year, so this is being, the interest is being compounded 12 times. So if we do the calculation for, what's her name, Julie. So n is equal to 15 times 12, and you can just type that in. I'm going to have to move this a little bit so I can see that keypad. 15 times 12. Interest rate was 90. Sorry, 9, not 90. Present value, so she's investing $1,500. Payment in, we're not worried about. Future value, that's what we want to find, so let's change that to a 0. She's going to be doing this monthly. And her compounds per year are monthly as well. So if we go back up to future value, alpha, and enter, we have 23, 48, 52, I think. I'm just going to pause here because I think I needed to leave that as a 1, not a... Okay, sorry about that. I found my mistake. When I was up at the top here at the N, when I initially calculated it, it went in as 5 times 12 instead of 15 times 12. So there's a 60 up there, but it should have been a 180. That's why it wasn't giving me the same value as I had. So the P per Y is the number of payments per year. So the number of times these interest will be paid out during the year. So that needs to be a 12. The compounds per year, because that's how many times this is being, how many times they're calculating the interest, so 12 times. So Lena will earn at the end, because she's only investing for 15 years, she is going to have $5,757.06. So that's for, not Lena, Jolie. So her future value is 5757.06. So for Lena then, her number of years, she is 18 and she's doing it till she's 65. So that's going to be 65 minus 18, which will be 47 years. And then times 12. So that, because the number n is your number of compounds per year, so that gives you your 12. So your interest then, everything else is going to be the same here except for future value. So let's see what happens for Lena here. So she's going to have 47 periods, or 47 years to invest, and number of periods that there will be is at 47 times 12. So 564. Interest is still 9. She's still investing $1,500. Payments are the same. And her compounds are still the same. Sorry, her periods are still the same, and her compounds are still the same. So if we go to future value, hit alpha, and enter. So at the end of her investment year, she is going to have $101,461.71. So the difference then is going to be 101,461.71 minus 57,5706. So $95,704.65 difference for the two of these ladies. So the B part says, Lena's older stepbrother Cody, age 34, also wants to invest $1,500 at 9% compounded monthly. Determine the future value of his investment at age 65. So whether you could use the future value one. So if you were going to do it with the formula instead of this, and I might as well show you at least one this way. So the n in this case is the number of compounding periods. So he's going to do it from 65, from 34 years. So that leaves him with, how many years is that? 31. So his number of years here is going to be 31 compounded monthly, so 12 times per year. The I then is that 9% at divided over those 12 periods. And our principal, of course, is that $1,500. So if you use the formula, he would have 1,500 times 1 plus 0.09 divided by 12 times 31 times 12 should be, I think, 372 if I did my calculation right. So calculating this way, you get $24,168.61. If you try it in the solver, so this one was 372. Same thing, 9%, $1,500. All the rest is the same, but we want our future value. Now, where did that go to? Alpha, enter. 24168.61. Perfect. Okay, next example. So Celine wants to invest $3,000 so that she can buy a new car in the next 5 years. Celine has the following investment options: 4.8% compounded annually, semi-annually, monthly, weekly, and daily. So it says, using the TVM solver, compare the interest earned by each of these options from terms of 1 to 5 years. Okay, so you could go through, I'm not going to do each one of these, but I'll do an example for a 3-year term and see what the calculations are. You could pick whichever amount of years you wanted to do. So if we looked at this for A is compounded annually, so our N here is going to be that 3 times 1. Our interest is 4.8%. Present value, so you are investing, that says $3,000. We want to find the future value. Payments per year is 1. Compounds per year, because it's annual, is 1. So if I go into here, move to the top. So our N is equal to 3 for this one. Interest rate was 4.8. Present value, we're investing $3,000. And make sure you use a negative and not a minus, because you will get a blip on that one. So our payments per year, it's once because it's annual. Go back up to future value, alpha, enter. So it's 3453.07. So I'm just going to switch my color here. 3453.07. So if we were looking this for option B, so option B, option B, everything will stay the same except our N. This is semi-annually, so that's going to be 3 times 2, so that'll give me 6. Interest is the same, present value is the same, future value we're trying to find. Payments per year, though, is 2, and our calculations, or our compound periods per year, is 2. So I'm going to change this one at the top. That one is just going to be at 6 because it's 3 times 2. This one is 2. CY is 2. Go back up to future value, alpha, enter, and we have 34. $58.76. So got up $5 by doing it twice a year. So what if we did it, the C is compounded monthly. So N is equal to 12. Our payments per year, sorry, not monthly, it'll be 3 times 12, so 36. Payments per year will be 12. Compounds per year will be 12. So our future value then, let's change this one to a 12, this one to a 12, up here to a 12 times 3, so that means the number of periods are 36. Go to future value, alpha, enter, 34, 63, 66. Okay, our D for this one then, I'm just going to scooch this over to the other side. So D was for compounded weekly. So for D then, that's a D by the way, number of periods then, so we're doing this for 3 years, and we're doing it weekly, so that's 52. Interest is the same, present value is the same, future value we're trying to find. Our P per Y is 52 times, and our compounds per Y is 52. So this changed to 52, PY 52, CY 52, up at the top. 3 times 52. Move down to our future value. Whoops, skipped over that. That's a lot of mumbo jumbo. So you do your alpha, enter, 34, 64, 42. And then the last one was if we did it compounded interest daily. So N is going to equal 3 times 365. So your future value you're going to find, your P per Y will be 365, and our C per Y will be 365. So up at the top, 3 times 365, 4.8, same down here. PY is 365, CY 365. Changed it automatically. I don't know if it did it the other times. I never noticed. Alpha, enter, 34, 64, 62. Oops, I forgot to do that in green. Again, this is green. 34, 64, 62. So you can see you're going to be earning more interest depending on how much your investment is. Well, I'm scared if I put this down I won't get it up for the next one, but we'll see. So you can see by doing it just annually, you had 34,000 or 3,453. If you do it daily, if you get a daily investment, then you're going to end up with $10 more per year. Okay, last page. Whoops, if I can turn my page. Our next page, I guess, not last page. Last page is just some info. So it says, both Bert and Chris invested $5,000 by purchasing Canada Savings Bond. Berta's CSB earns 8% compounded annually, while Chris's earns 9% compounded annually. So it says estimate the doubling time for each CSB. So this is where we use that rule of 72. So if you remember from the beginning, the rule of 72 says you take the interest rate and you divide it into 72, and that'll tell you about how long, approximately how long it'll take to double. So for Berta, she is taking 72 and she is getting 8%. So it would be 9 years approximately. For Chris, he's taking 8 years, or sorry, 9%, so that would be about 8 years. It says verify your estimates by determining the doubling time for each CSB. So what we would do then is on our TVM solvers, what we're going to calculate for this one is our N. So our I, interest rate, so we're doing Berta first. Hers was 8%. Present value, they're investing that 5,000, so minus 5,000. Future value, we want it to double, so that'll be 10,000. And this is an annual one. So PY is 1 and CY is 1. For Chris then, our N is what we're finding. Our I though will be 9, and then everything else will be the same as Berta's. So let's bring up the calculator here and see what happens when we give this a try. Okay. I don't need the keypad history because we already know what we're doing here. So, N we don't know, so let's just switch that to 0. So for Berta, it was 8%, and the initial investment was 5,000. We want a future value to be 10,000. And it's just once a year because it's annual. So go back up to interest for Berta, alpha, enter, 9.0. Well, 00, so 9.01%. So if I do this now for Chris, let's put a 0 there for right now, change this to a 9. Everything else is the same. So it's $5,000, present value, future, we want 10 annually. So go back up to the number, alpha, enter, and you get 8.04. I shouldn't put percent, that's years. So you can see the rule of 72 worked for it. So it says estimate the future values of an investment of $5,000 that earns 8% compounded annually for 9, 8, and 27 years. How close are your estimates to the actual future values? Okay, so we're taking 5,000 and we want it to be 10,000. So 9 years, where are we? Estimate the future value of an investment of 5,000 that earns 8%. So 9 years, whoops, I need to move my page up here. So in 9 years, we want there to be $10,000. In 18 years, then, we want there to be $20,000 because we want it to double. And then again in 27 years, sorry, I should have done this first. So using a rule of 72 at 8%, so every 9 years it's going to double. So at 9 years we'd have 10,000, 18 years we'd have 20, so another 9 years to double means we would have 40,000 then. So what the question is asking then, how close are what is the future value of an investment So we're saying, using the rule of 72, in 9 years it would be 10,000, 18 years it would be 20, and 27 years we're saying it would be 40,000. So we can check this using the TVM solver by saying that our N is 9 years, our interest is 8, present value, so we're starting with that 5,000. What is our future value going to be? And again, these are being done just annually. So if I try that on here, our N for the first one was 9 at 8%, investing 5,000. We want our future value to be 10,000. No, we want to find our future value, sorry, put this to 0, 1, 1, K, or, so now, alpha, enter, for 99, so by calculations then, your actual interest or your actual future value would be $9,995.02, so $5 off the double. So let's check to see if in 18 years, we have $20,000 like it says here. So everything is going to be the same except our N is 18. So go back to future value, alpha, enter, $19,980.10. So if our N was, we're saying in 27 years, it will have doubled again. So our future value then, move up 27 here, go down to future value, alpha, enter, so it should be close to 40, and it says it's $39,940.31, so pretty darn close, I would say. Okay, last part for this very long section. So, just to recap, future value of an investment that earns compound interest, our basic formula is A is equal to P plus 1 plus I to the N. A is your future value, P is your principal, I is the interest rate per compound period, expressed as a decimal, and N is the number of compound periods. So it says the more frequent the compounding and the longer the term, the greater the impact of compounding the principal and the greater the future value will be. So all it's saying there is the longer you leave something in for and the more periods that there are, then the more money you're going to have. So it says when using the compound interest formula, use an exact value for I. For example, for an interest rate of 5% compounded monthly, substitute 0.05 divided by 12 instead of rounding it to 0.0416. So that's why when I was putting the questions in there, if it didn't work out to an exact value and it was rounded, you put it in your calculator as that fraction value so that it can give you a more accurate answer. 4 common compounding frequencies are given in the table below. The table shows how the interest rate per compound period and the number of compounding periods are determined. So this is just kind of a nice little need to know for you, summed up nicely. So annually means it's once per year. Your I is equal to your interest rate, and your N is just your number of years. Semi-annually is 2, so you take your interest rate, divide it by 2, take your number of compound periods and times it by 2. Quarterly, divide by 4, because that means it's 4 times a year, or multiply by 4 for number of compounding periods. Monthly is 12. Total compound interest earned on investment after any compound period can be determined by using the formula I is equal to A minus P, so just future value minus your principal, or P times 1 plus I to the N minus 1. The rule of 72 is a nice strategy when you're trying to figure out how long it'll take for an investment to double. It is most accurate when the interest is compounded annually. For example, $1,000 invested at 3% compounded annually will double in approximately 72 divided by 3 or 24. And $1,000 invested at 6% will take 12 years. So your questions are down at the bottom here. Good luck. Use your TVM solver where you can, but also make sure you're practicing these with the formulas as well.